So in the previous video for chapter 15.1, we basically talked about general acid and base properties and how to name binary and ternary acids as well as bases. So this is the continuation of that information. So you can have a strong and weak acid or base. A strong acid or base basically means that it ionizes 100% in a water solution. And a weak acid or base means that it ionizes less than 100% in a water solution. And remember, to ionize means to break into ions. So the hydronium ion, which is H3O+, is basically what gives acids their properties. So the presence of that positive ion, a cation, is what makes acidic properties occur. So sometimes you will see that H3O+ can also be called a hydronium ion. It can also be called a proton. It's not a subatomic particle proton. It's just referring to the positive charge of it. And just recall, a cation is any positively charged ion due to the loss of electrons, and because of that, you're losing negativity. So any positive ion is a cation, and H3O+ can also be called a proton because it's positivity. So acids ionizing in water. So you have water, H2O. You have an acid. The water is going to give a proton, an H, as we will say, to the water. Let me say that again. An acid is going to give a positive proton, an H, to the water. H2O becomes H3O+, positive. And then the acid breaks down into a negative, usually metal. So if you look at the picture over here, that's showing you just the proton being given to the H2O and making it H3O positive. And then this picture is just showing you HCl breaking apart into its ions. Once again, the H2O accepts this H+ proton. The Cl is left by itself. So in ionization reactions, you have to label the acid and the base. Remember, acids usually start with H. So HCl is our acid, hydrochloric acid. And in this case, water is our base. Water can be an acid or a base, it just depends. And it yields H3O+ and Cl-. So once again, this acid is going to ionize, break apart into ions. The H becomes positive, the Cl becomes negative, and the water picks up that positive H. So the H is given to the water, and it's now H3O positive, and chlorine is negative. So when you're showing ionization reactions, be sure that you're labeling the acid and the base and actually showing what happens. So this just kind of explains it. So the H and the Cl and the acid separate. The H is donated to the H2O, which accepts it. So the water accepts a proton, if you will, as far as H goes, and it becomes positively charged. H2O becomes the cation, and it leaves behind chlorine, which becomes the anion. We know the positive and negative tract. Okay, so once again, just practice writing these. So in the first one, we have HBr, hydrobromic acid, and water. Once again, hydrobromic acids are acid, water's our base. So once again, the H is given to the water. It yields a hydronium ion and a negative bromine ion. If you have more than one H, only one H is donated. So you have H2SO4, which is sulfuric acid. It's our acid giving a proton to the base. So you only give one H. So there's two here. Only one is given. So you still have hydronium, H3O+. You're always going to have that. And then you're still left with an H, SO4, which is minus. So if you have more than one H, only one is given and accepted by the water. Okay, so this is just general ionization reactions. We don't get really more in depth than that. The hydroxide radical, which you're more familiar with just from your radical sheet, is OH-. So this is what gives bases their basic properties. You can also refer to basic solutions as alkaline solutions. So you may have heard that before. It's popular to have alkaline water. It's a basic water. And then just recall an anion is a negatively charged ion due to the addition of electrons. We use this term for any negative ion. Okay, so actually doing a base ionization in water is a little bit simpler. So if you look at this picture right here, you have NaOH, sodium hydroxide, a base, and basically what happens is it just splits apart. Splits into Na and OH. Nothing is accepted by the water, so we just say it's in an aqueous solution, meaning a water solution. So that's why we have AQ here in parentheses. You have to include that, meaning in water, because water is part of the equation and it's not represented on this side. So that's why you put the AQ. So basically what happens in a base ionization reaction is you have the base, it splits apart, the Na becomes the positive anion, or positive ion, the cation. OH, the hydroxide ion, is the negative anion. And like I said, the water is still present, you just put in aqueous solution. Yes, you could technically write plus H2O over here, but it's not as accurate. So base ionization reactions are definitely easier to write. You always have the metal becoming the cation, positive, and the OH becoming the negative anion, and then in aqueous solution. So once again, Na and OH separate into their ions. H2O does not accept the ion into itself, so the ions just are in the water. Water doesn't change in this realm. Okay, so once again, a strong acid is going to ionize 100% in solution. Usually there's weak bonds which allow the ions to break apart, and it's usually polar. I don't get much more into it than that right now. We just don't have time. So here are some examples of strong acids. Sulfuric acid, hydrochloric acid, hydrofluoric acid, hydrobromic acid, nitric acid, hydrogen or hydroiodic acid. I don't get into why they're strong, just pick a couple and know they're strong. On the other side, weak acids, they ionize less than 100%, and here are some examples. They usually have more H's involved, but not always. Okay, and then bases, once again, strong bases, ionize 100% solution. This is going to be a group 1 or 2 metal plus the hydroxide ion. So here are some examples of strong bases. A base doesn't have to have an OH on it though, and you'll see what I mean in a minute. Strong bases do have the OH hydroxide ion present. So you've got sodium hydroxide, calcium hydroxide, lithium hydroxide, potassium hydroxide. Those are also all very strong metals in the base itself, very reactive. So strong bases are always going to have OH. Weak bases, on the other hand, do not ionize 100% in a solution. And the best examples I can give you are ammonia, which is used for a cleaning solution, and some things like that. So they're weak bases. That doesn't mean they're safe. It's just they don't ionize as much in solutions. Okay, and that is it for 15.1. Like I said, I know it's a quick kind of overview, but I'm just giving you the big points to kind of get a realm around, or wrap your head around acid and bases.